Hey students, we are checking connections 3.2. 3.2 looks like we got 1, 2, 7, 9, 13, and 13 through 16. So if we take a look back here, 1 and 2. So let's see here. Question 1, in a survey of 52 students, 22 said algebra, 30 said they're taking biology. Does that mean there's 52 taking algebra or biology? Oh, wow. So this ties right into what we were talking about, both in chapter 2 with sets, but also here with the definition of addition with the set model. So I'm going to leave that up to you. Does that mean there have to be 52? Okay, now remember, just because there's 52 students, you got to answer that question. Let's see here. To find 9 plus 7, a student says 9 plus 7 is 9 plus 1 plus 6, 9 plus 1 parentheses plus 6, 10 plus 6, and 16. Okay, so this question is saying what property or properties is the student using? So this is your chance to kind of shine, if you will, where you can say, okay, I know exactly what the student is using. Oops, gotta plug this back in. There we go. What property or properties are they using? So for example, what property allows you in this first step to regroup the parentheses? What was the name of that property? Okay, so if I was doing this like on my paper, I probably, let me come down here and pull some white space here. Okay, I would probably rewrite this personally, and I would say, okay, so I have 9 plus 1 plus 6 like this, and then put an equal sign and say, okay, now that is supposed to equal this. Okay, and so what you're doing is you're saying to get from here to here, from the first step to the second step, what property did I use? Okay, so which property allows me to regroup? Okay, and so you list a property here. Then say, okay, now from here, 9 plus 1 is 10 plus 6. Now, again, you're saying what got me to the next stage? Now, if you need to, there are some pieces in the textbook. I want you to become more familiar with them as to what properties are named, because we will be using them by name as we keep going. But that's kind of the piece that I want you to try for that question. Okay, so that's 1 and 2. And let's see, you're turning the spotlight on. 1 to 7. Okay, question 7. Discuss the merit of the following expanded algorithm for addition where we add the ones, tens, and hundreds, then the total. Okay. All right, so you're trying to say, hey, what do I like about this? Why is this technique kind of a good technique if I was teaching addition? Okay, so what are the benefits? And hopefully you can see some benefits. I can see quite a few benefits here. If you're comparing this to the traditional algorithm where things are kind of floating above numbers, I think there's definitely some confusion that comes from that. Maybe this technique doesn't have any of that confusion. Okay. Let's see here. That was 7. Was it 9? 9. Okay, 9. In the new textbooks, there's an emphasis on mental mathematics and estimation. Explain why these topics are important for today's students. Yeah. So I've noticed that a lot of future teachers, I'll say, so this is people coming into the STEM Learning Center over the past few years, they would say, I don't know why I need to know this. I can just put it in a calculator. I can just use a computer. And I won't disagree with that. The arithmetic skill of a calculator is usually above what we do. I guess I would say, if you think about it, why do you need to know mental math or estimation? Is you should be able to get pretty close. You should be able to tell whether an answer is reasonable, right? That might be something, right? If you were supposed to add together a bunch of numbers and they all start with a 1 and you accidentally typed one of them backwards, which does happen when we're doing things quickly. So like a 12, a 15, a 17, an 18, a 19, right? You got all these numbers here, and all of a sudden you look at the sum, and let's say there's 8 of those numbers. By using a little bit of estimation, 8 numbers, all between 10 and 20, make them all 20. You've got 8 times 20. That's 160. So right away, I know there's no way I should be above 160. I should actually be below 160. So if someone tells me, okay, I add those up and I get 215, I would immediately say no. Something went wrong. And I think that's what I want you to emphasize here, is that you need to know when something goes wrong. And lastly, 13 through 16. So Zeke claims can get the same answer to the problem by beginning with the 4 and the 7 and adding down as by beginning with the 8 and the 7 and adding up. So adding up or adding down. Question to you is, what do you say to that? Is that going to give you the same answer? Now, again, it's not just about yes, it's the same. This is If your answer is yes, then that doesn't help the student. Why? Okay, so we've got a how and a why. What is mathematically correct or incorrect? Is the student on the right track? Probably a little bit of praise, because at least the student is curious about something and trying something on their own. And then finally coming back to, let's talk about the terminology. What words, properties, theorems, what is guaranteeing that it does work, or what is demonstrating that it does not work? Okay. Child was asked to compute 7 plus 2 plus 3 plus 8 plus 11. Oh, very common, right? To do this, it's written horizontally, so the student writes it horizontally. And so then at the end of the day, the student ended up with equals 31. And this says, if you were the teacher, how would you react to seeing this written out by a student? Okay, so you could say, oh, it's totally correct. I don't see any issue with it. Great job. Keep it up. You're doing a great job. You could say, oh, you've got the right answer at the end, but let's make sure we're writing it correctly. Or you could say, oh, you've got the right answer, but you actually made some mistakes along the way. Again, I'm leaving that part up to you, because if you were a teacher, how would you react is the question for you. Let's see here. When Richie was asked to round this number to the nearest 10, wrote 2578. Again, a pretty common answer. I know some of you be like, how would that ever happen? Again, rounding to the nearest 10, what would you do? And so you might be saying to yourself, well, if it's round to the nearest 10, then you would round up. So you would round the 6 up, for example, right? Well, if you round the 6 up, doesn't it turn into a 7? So if you think about it from a student standpoint, they heard exactly what you said. So you may have to respond a little bit in saying, hey, if you're rounding, let's think about the concept, right? What is the concept of rounding? Perhaps a drawing would be helpful. Again, these are 13 through 16, the connecting math to the classroom, these CMC questions. These are the bulk of what I'm looking for. How do you respond to students? How will you respond to students in the future? Okay. And then the last one, and this is actually a common one, not just for elementary school students, this goes into adulthood as well. Ashley was asked to round 345 to the nearest 100. So she rounded 345 to 350. So she rounded to the nearest 10. Oops, got my alarm going off. And then rounded 350 to 400. So done. But Billy's over there, and Billy, I wonder if this is like music singers. Like, isn't it Billie Eilish? Something like that. Ashley something Simpson, whatever. Anyway, they do things like that. Teachers do that because they get bored writing all the questions. So sometimes they take people from the from the press. Billy claimed the answer was 300. So how do you respond? Is one of them correct? Are they both incorrect? What is the idea of rounding? So again, you're going to be covering the concept, because we're making a connection between the idea and what the student is actually saying. And then I think I had one more on this one. Group work number 2, but you just don't need any group. Okay, so let's see here. What would that look like? Student book pages, click forward. And here we go. Oh, group work. Yes. Okay, so I want you to do question 2 right here. Suppose a mathematical system uses only 4 symbols, an A, a B, a C, and a D, with the operation delta or triangle as shown on the table. Discuss this with your group. Well, you don't have a group, right? You have me in a video, or I mean, you're welcome to talk to other people, but I really don't think you need a group for this. So when you look at this, what this is saying is A, triangle A is equal to A. Now, some of you are going to freak out a bit because you've never seen a triangle as an operator, but I want you to picture this. You've seen this symbol as an operator, and the first time you saw it, you could have said the same thing that a child might say if they saw a triangle as the operator. You'd say, what the heck is that? So you got used to these symbols at some point in time, but they were new at some point in time. And I am putting you in the boat of seeing a new symbol and trying to figure out how it works. I'm also removing the idea that you know what the numbers represent, because again, as a child coming into this, they may not completely understand all of what happens with numbers. So my goal with this question is to put you back into the place where you're kind of like learning like a child would. So next one, B triangle A, that's right here. B triangle A is B. Okay. C triangle A is C. And I can see that right here. Here's C, goes up to A, and I get C as my output. So just like when you were doing your math growing up, the outputs are sitting here in the middle. Those are all the outputs. And so you kind of go over for rows and columns. So if I want a D triangle B, I would go to D, I would go to B, and then I go down to where those meet, and D triangle B meets here at A. D triangle B is A. Okay. So you have some questions about this system. That's what I'm asking you to do. Is the system closed? Okay, is it closed under the operation of triangle? And why? So you need to answer each one with why. Is it commutative? Remember what commutative means. Go back if you need to, but have this more at your fingertips. Commutative. If you're struggling with commutative, think about like driving from point A to point B, right? The distance from here to here, the distance from here to here, the distances are the same. So this is like your commute. And your commute, so for commuting items, commutative property. So forwards and backwards would be the same. Is it commutative? Use several examples to investigate whether the operation is associative. Now for part D, I'm okay if you wanted to do like 3 examples and kind of say, okay, I can see it is. Associativity is the longest one to check because you have 4 symbols you could put in the first one. So if you think about what do we have? Triangle B, triangle C. So here's kind of the associativity, right? We're trying to see if this is the same as this. We're trying to see that, and we don't know. So if you're regrouping, though, you could put any symbol in for each of these boxes. That means there's 4 options first, 4 options second, and 4 options third. That means if you were really checking every little piece here, this would be 64 individual things that look like this you'd have to check. And I do remember that when I was in grad school, and I remember a teacher said, why don't you just check associativity works? Oh my goodness. We actually had, thankfully, we got to use some computer programming so that we didn't have to start from scratch. But we had a set that was a little bit bigger than that. So we had 10 items. So there would have been 1,000, 10 times 10 times 10 individual pieces we would have to check. And maybe one of them fails. And if one of them fails, the whole thing fails. So that's the piece to do there. All right, so there we go. Oh, and by the way, I did talk earlier about the addition table for different number bases. This is the addition table that you might be used to from your own schoolwork, right? So this would be the base 10 table. But look at it. Look at the patterns. This thing is so rich with mathematics. Look at the patterns, right? If I want things adding up to 2, take a look, right? One. So here's all the ones. Here's all the 2s next to it, right? 2, 2, 2. So we can kind of figure this out. What's great about this is that, like, if you were teaching, you really could say, okay, students, this entire chunk down here, this entire chunk, you really don't have to learn it because this entire chunk up here is identical. Okay, so that's the commutative property, right? If you look at it, 4 plus 1 is the same as 1 plus 4. And so those mirror each other. We get this beautiful reflective symmetry. It's just reflected over the line. And the line, what's in that line? The line is the line of all the doubles. Look at it, 2, 4, 6, 8, 10, 12, 14, 16, 18. So the line of perfect doubles, when you add a number to itself, there's no mirroring that because there's no other way to get 3 plus 3 in the picture. But for every other symbol, any time that you have a, what is this, 3 plus 8? Well, guess what? You've got an 8 plus 3 right down over here, and they mirror each other. And of course, they're both on that line of 11s. There's a lot of other things that get you 11. So if 8 plus 3 works, then 7 plus 4 works, then 6 plus 5, then 5 plus 6, and then 7 plus 4. And it keeps going in that way. So it's, again, these tables may look pretty basic and simple, but there's a lot of mathematics going on inside of them. And part of this class is getting a chance to do those. All right. That's it for the MCs. I hope you all have a great day. Off you go.